Jen actually was the chair when he was nominated for the award, and she nominated him. So we appreciate all of your dedication and hard work to the section. Now I will pass the torch to David Godfrey to introduce the Herty Award medalist.
So I actually wrote out my remarks because I've only been doing this for a year, not like 10. So first before I begin to introduce our medalists today, I wanted to thank the members of the Herty Selection Committee, a few of them who are here, David Lynn, Joanne Arsenault, Brian Lawrence, Mark Mitchell, Lily Harvey, and Ajay Mulligan. Thank you for all the work you did. So 2017 marks the sesquicentennial, that's 150-year anniversary of Charles Herty's birth in 1867. And you can read all about Charles Herty in the program and more in the citations that are given there. But he was a true Renaissance man. So he not only was a professor of chemistry at UGA and the football coach at UGA, he worked for the U.S. Forestry Service. He chaired the Department of Chemistry at the University of North Carolina. He served as ACS president twice in 1915 and 1916. He was the founder of the ACS News Service, which became, we all know, as CNE News. He helped establish the National Institutes of Health, and he was one of the main proponents for advancing the chemical industry in the United States in the first half of the 20th century. So, and that's just a subset of the things that he really accomplished. Since 1933, this section has awarded the Herty Award to a Southeastern chemist who, making this one of the oldest multi-state regional award from the ACS, correct, Don?
Second oldest.
Second oldest.
Okay, second oldest.
No, wait. It's the oldest multi-state regional.
That's why I said that.
It's the second oldest
ACS
of any kind of award.
Right.
In ACS. That's open to everybody.
Right. So, and as you'll see, the inscription on the gold medal that we award is Pro Scientia et Patria. My Latin is not very good. For science and country, which was Herty's motto. And when we go through the nominations, we really take this to heart, and when we're looking to choose an outstanding chemist who really demonstrates both of these traits, breaking ground in novel science, while at the same time serving the profession and society through education, outreach, and service. And so therefore, it is a true pleasure and privilege that we are honoring a longtime friend, colleague, and member of this section, the Georgia section, Professor Rigoberto Hernandez. A few brief highlights from his biography. Again, you can read more in the program. Rigoberto got his bachelor's degree in chemical engineering from Princeton, then his PhD in chemistry from UC Berkeley, did postdoctoral work at the Weizmann Institute in Israel and at the University of Pennsylvania, and then came to Georgia Tech, where he joined the School of Chemistry and Biochemistry in 1996, and stayed here for 20 years before moving on to Johns Hopkins, which, in analogy with Herty, did his undergraduate work at UGA and then went to Hopkins for his graduate work. So again, moving from Georgia to Hopkins. So, and where he is currently the Gompf Family Professor in the Department of Chemistry and also continues something he started in 2011, which is as director of the Open Chemistry Collaborative in Diversity Equity, also known as OXI. I won't go into his research work too much, except to broadly describe it as in the area of computational chemistry, focusing on the effects of molecular behavior on overall system attributes. He's a fellow of the ACS, the APS, the AAAS, and has won a number of awards both for his scientific and service contributions, and has served the ACS in a number of roles, both here, certainly at the local section, and nationally, where he's currently district director from District 4, which is the district that we're in currently. In the words of one of his nominators, and this is a direct quote, "He truly channels the broad portfolio of Charles Herty and brought tremendous recognition to the Southeast ACS region over the past 20 years." Unquote. And finally, while I know it is a bit coincidental, I want to mention one other interesting connection, and he knows where I'm going with this, between tonight's honoree and Charles Herty. So I mentioned that that 2017 is the 150th anniversary of Herty's birth. Exactly 100 years after Herty was born on December 4th, 1867, Rigoberto Hernandez was born. So this year, he not only reaches the big 5-0, but he is also this year's 2017 Herty finalist. To regale us with his medalist address on diverse chemistry topics and the diversity of chemistry.
Thank you, David, and thank you everyone for being here. There's lots of things that you can do on a Thursday night in Atlanta, and oh, no, you're good. There's a lot of things that you can do on a Thursday night in Atlanta, and I appreciate that you're sharing your time with me and with each other. I wasn't sure what I should talk about, so I'm going to tell you a little bit about everything in a buffet. But I'll try to do it in briefly. And in many ways, David has already given about a third of my talk, as you'll see. So I am the district director, and this is the map of the states that correspond to the district. The way that the American Chemical Society divides its local sections is to roughly even out into 6 portions. So there's 6 districts. What's happened with the U.S. population over the past few years is that it's grown far west and south. So the district used to be here, and it's grown into including Texas. And this might explain why the Herty medal states are limited to more of the southeast, which includes, in this counting, Virginia, West Virginia, and Kentucky, and did not include Texas, which is something that you might want to know from the history. So to me, I think that there is something to be said for the Southeast, and the fact that Atlanta as a capital of the Southeast has really grown over the last 100 years. And I think it's something that the Georgia section can be proud of, and that we can leverage and also advance the science. It's part of what made Charles Herty, I think, so notable, and that's why the section started honoring him, because he was not just a scientist, he was also advancing the country. As was just mentioned, he was born in 1867. This is his 150th birthday, so it's quite notable, and I very much appreciate the luck and happenstance of being named a medalist on this birthday. His PhD was from Johns Hopkins, and it was with Ira Remsen. It turns out that Ira Remsen, who obtained his PhD in Germany, learned the way that the German system had trained students, had trained PhDs, and brought that notion to the U.S., and in many ways was the founder of the modern graduate education in the programs in this country. And Hopkins was among the first to award, if not the first, to award chemistry PhDs. There are other chemistry PhDs from that program that came to Georgia, and Charles Herty, being one of his students, is one of them. So to me, that feels like another connection that we have between Georgia and Hopkins, and somehow dovetails with my own career, which is surprising and exciting. He was an innovator. He developed the so-called Herty system to extract turpentine from longleaf pine trees, saved the wood industry. It's part of the pulp industry in Georgia in the Southeast. It's part of what led him to be part of the U.S. Forestry Service. He founded the Savannah Paper and Pulp Laboratory in Savannah, And I believe that one of us here, maybe his name is Don Hicks, was critical in establishing this as a National Historic Chemical Landmark, and went to Savannah as part of our efforts to expand the mission of Herty some years back. He was a science builder. He was a chemistry department chair. He served as ACS president not once, but twice. That wouldn't be possible today, given the rules of how people become ACS presidents. So he has a notable distinction of probably being maybe one of the few, if ever, that served for 2 years. He was the scientific advisor for the Ransdell Act, and that is the act that established the National Institutes of Health. And so there is not just a connection to industry, but also building academia, building sense of science and community. And it's for that reason I believe that the Herty Medal, which you see depicted here, was founded by our section. We had a connection to Georgia, through Georgia to him, and also he was someone who truly epitomized this idea of proscientia et patria, that is for science and country. And so the scientia would be the contributions to the profession, which is one of the requirements that our section has always looked for in medalists. And then the patria, and this should, so the scientia is the science accomplishments, this is mixed, and the patria is the contributions to the profession. And I thought about this and I thought, well, what's the NSF criteria for a research grant? It is intellectual merit, that's the scientia, broader impacts, that's the patria. So not only did he found the NIH, he anticipated through this award what the NSF does. All right, so take that one, Don. You can add that to the things that Herty did. And so when I think about that, it just makes me feel all the more honored to be recognized for this award and to join David Lynn, who's in the audience, past medalists, and all of the other medalists that have been recognized for the things that they have done. From Georgia Tech, Gary Schuster, Jim Powers, Leon Zalko, Dean Ashby were all medalists that I interacted with over the last 20 years when I was at Georgia Tech. I did not get to meet Jack Hine, but I sure heard many stories about him from Larry Tolbert, for example, who was Liddy Harvey's PhD advisor. So the connections that we have with where we are really are deep-seated. And then I think about diversity. And indeed, I was the chair of the Herty Award Selection Committee for about 11 years. Taught me a bit about his history, and also about the history of the award, how many white men had been recognized in the Southeast. But it was not because, which is good, you know, do good science, you should be recognized for it. But maybe others should also be part of the program. And so you see when you look at the list, Greg Robinson, Lucia Chigoyan, Isaiah Warner, Ernest Elio, who actually received his degree from the University of Havana, not Hispanic or Latino himself, but had a connection to Spanish-speaking countries. Diversity. And one of the things that I've enjoyed in my career is thinking about different types of science. So when I was a PhD student, I toyed with the idea of being an experimentalist. And I love doing experiments because I love machines. I love to play, my wife knows I do all the plumbing and the electrical work in the house. The trouble was that all of the physical chemists or experimentalists, they spent a lot of money building really big machines. And once they built that machine, what did they have to do? Use it, right? And so now that means that they had to find a problem that they could use their machine on. And I thought to myself, but what if I want to solve a problem that my machine doesn't work on? What do I do then? As a theorist and a computational chemist, I can change my machine on a dime. A problem comes along which is interesting and fun, and I can attack it with the methods that others have developed with computing and software, We all do shareware these days, so I can use those tools. I can develop some tools, and I can put them together to solve a new problem. And so really what drove me to be a theoretical computational chemist was that I wanted to think about really broad and different types of problems. Now there's a challenge in that because that means that you have to get funding on different types of problems. So that can be a problem. I've been fortunate that I have been able to recruit students, and because of the broad training that we received, they're able to have jobs that are very rewarding and in very different fields. So I'm going to tell you a little bit about these topics through 11 vignettes, and each vignette is just one page. So we won't have that many slides, but we'll give you a taste of that diversity. To set the stage, what we do is roughly dynamics in complex environments. The way to think about this is I want to understand chemical events, not just at equilibrium, but when they're moving, in motion, dynamics, in an environment that itself is broad and moving. So we can't just think about a chemical reaction in a water solvent, just in water, and ignore the water. You do this actually all the time. When you think about swimming in the ocean, you don't care about how many sharks are nearby as long as they don't bite you. Right? But if the environment is difficult and complex and it does start to bite you, you need to think about how that changes your environment and how maybe others coming in, let's say somebody has a little bit of blood, gets another shark out there that you didn't anticipate. So we want to think about a chemical environment that's complex, that is heterogeneous, and think about the chemistry that's going on inside. So that's why we call it dynamics in complex environments. And if you are about 15 years old, you can tweet about it as we go along. You can tag me at everywherecam. And you can put whatever hashtag you like, not pound. Okay, that thing is a hashtag. And so just be aware of that. So what do? So we have to have some types of methods. We need to have targets that we address, and we have challenges. So this evocative triple is the one that we use to think about how, one, we divide our work, and two, how we connect it. You may have heard of chemistry through this other evocative triple, which is make, measure, or model. There are people who make molecules, there's people who measure it to see what it does, and there's people who model to understand what it does and predict new ones. And there are people who do all three, but it's a loop. We need makers, measurers, and modelers. I like this evocative triple because it makes me think that I don't have to be an organic chemist or a physical chemist or an analytical chemist that can't talk to each other. We're all chemists. And how do we then connect with each other? Well, it's the same targets. We want to understand nanoscale materials, biological materials, sustainable materials. I use theoretical and computational chemistry as my tools. You might use other tools. In that theoretical and computational chemistry, I have to use analytical techniques, that is equations that I have to solve. If I solve them directly, I'm using computing to basically grind out the equations. Or on a computer, I can do a simulation that helps me understand the system. That's a kind of a numerical experiment. So I can use computers in different ways. All of these are my tools. What's my challenge to success is this idea of length, time, and complexity. A molecular or chemical event occurs on the order of femtoseconds or smaller. Especially if you like electrons, then it's a lot smaller than a femtosecond, maybe an attosecond. And yet humans don't think in femtoseconds. We kind of think about seconds, minutes, years. That's 10 orders of magnitude in separation. The distances of atoms and molecules are angstroms to nanometers. Humans are more like meters, another order of 10 to the 10th orders of magnitude. How do we go from those small scales to the human scales? That's the fundamental challenge. And if it was simple, that means we could treat every single one of the events acting in the same way just many times, then we'd be okay. And every chemist in the room knows what that would mean is that we would be an ideal gas. And we would never be any other type of state, right? So if we want to move away from ideal gases, we need to have interactions in complexity. So it's the problem, but also the opportunity. So this is what rules what we do. And in one example of what we do is we're looking at sustainable, working with the Center for Sustainable Nanotechnology to try to address those many length scale challenges from angstroms to meters. In this case, my students, Kaylee Allen, Ali Randamoon, Jean Chong, undergraduates, Anthony Batista, and Nikita Rozanov, and I'll go through and I'll tell you many names as we go along. What we're doing is initially using molecular dynamics simulations, And ultimately, using coarse-grained simulations, trying to understand how to control those so that we know exactly what those time scales are and position scales, to be able to predict things like how nanoparticles get together, how do they interact with an interface, and perhaps even change the chemistry of a cell. Why would you want to know whether it changes the chemistry of a cell? Well, that's because these nanoparticles that are being made today might be toxic. Right? We have problems in earth, in water, in energy, in health that we've created in some cases, or from previous solutions in the past. Let's say when we had the Industrial Revolution, or when we had the Iron Age, etc. We created environmental concerns. We don't want to repeat those. How are we going to solve those environmental concerns? We're saying let's use nanoparticles. But if those nanoparticles have deleterious effects to the environment, we solve one problem while creating another. So the objective of our center is to develop these nanoparticles that are benign by design. Not only do they provide the function that we need them to do to solve a problem, but that they don't introduce new problems. Okay? That requires a large number of people, that you see shown here, from many different universities with many different tools. So some of them are experimentalists that study the materials, or they make the materials, or they look at the toxicity. So some of these people are marine biologists. So the fun of being in the center is that we're thinking about a lot of different scales and using all of our complementary techniques, because while we have different tools and different challenges, we're working on the same problem. Another example of work that we've been playing with is advancing transition state theory. So in chemistry, we like to understand chemical reactions. We want to know when a reaction happens or doesn't happen. And we want to know, and one answer of knowing whether it happens or not is if the free energy difference is lower. And so all we need to do is know an energy difference. However, if it takes the age of the universe to go from reactant to product, it won't ever happen. We need to know the time, and we need to know the pathway. And so transition state theory, which is now over 100 years old, recognized that if you knew the barrier, that maybe that was enough. And now, to know the rate, all you need to know is the energy difference between the reactant and when you are reactants and this barrier. Okay. Just like if you want to go over to the nearby town, if there's a mountain in the way, you try to find the smallest pass, that col, so the chemical reactions do the same. So the question is, if you only focus on that geometry, that structure that is between you and the products, you might not necessarily know everything that happens. You might not get the exact rate, just because the processes might go over and come back. They have all these sort of meandering paths. When working with my students and many others, we've developed techniques to be able to identify what that dividing surface is between reactants and products in a way that's exact. So we can take a transition state theory that was formerly approximate and make it exact. Now many people have worked in different parts of this. In fact, Joel Bowman, who's in the audience, he's done some beautiful work identifying that sometimes those paths are really, really far away. And they roam, just like on the plains. And the question is, one of the questions that we were able to play with was to identify if there is roaming, how do we reconcile that with transition state theory? And so that, in that way, we can basically make the theory stronger. And so that work was with Inga Olusoy, who's now a research scientist at Michigan State University. Another direction as we go now in scale. So those two problems were in the smallest length scales, just thinking about a few atoms and molecules. Now if I take a solvent and I put an atom or molecule in a solvent, I have a small problem. I want to understand this reaction in a solvent. I'm only maybe interested in 5 or 10 or 15 degrees of freedom, but my solvent gives me hundreds to thousands more degrees of freedom, maybe hundreds of thousands. Those extra degrees of freedom make the problem harder to solve. And interestingly, I don't really care about them. I only care about the 5 to 10 that are reacting. So can we or should we somehow include the solvent in a way that is simpler? And so we developed a model called the stochastic hard collisions, where we literally pretend that the solvent is like pool balls. And these pool balls can go inside of each other and through each other some of the time. But when they're not, when they're far away from each other or not touching, they have no interaction. By controlling the degree to which they're able to go penetrate, we're able to control roughly their interaction, as if they were soft particles, mushy, squishy particles, which particles really are. And then we can ask questions about the solvent, the reactions inside of it. So this work initially started with Galen Craven and Alex Popov. Now is with Ben Mahala and Rakesh Singh. And we've been able to identify what the structures are, how it depends on dimensionality, and how we can even control what those interactions are with these very simple models. This was partially motivated by this other model, which started with Matt Hagee, who was a PhD student with me at Georgia Tech, now is a data scientist in San Francisco, and then taken up by Jean Chong, a new graduate student, Saurabh Hazarika, and Rakesh Singh as well. And the idea here was, if I have particles that are like spheres, but they're somehow structured, that is, they have a different type of interaction on one side than they do on the other, that's what the red and the blue are saying, then do they restructure or do they relax in ways that are controllable, or that we might be able to predict? And by being able to control the structure on the sphere, maybe you can control the solvents that they make, or the structure that they make. There was evidence that this happened in small clusters. What we were able to do was to take it into a solution of them, so that you see here in this simulation that they're moving, and we were able to obtain the relaxations. And what this allows us to do is to then ask questions like the following. If I have a system where the particles are red-blue, that means they're structured. If I can approximate them by green particles, which means they're not structured, but with the right approximate interaction potential, can I get the same structure? This is an example of coarse graining, removing degrees of freedom that you might not need. When you remove those degrees of freedom that you don't need, the bad news is that you can't ask about the ones that you got rid of. Okay? But you can still ask questions about the ones that you kept. That is, what's the relative positions of those particles? It turns out that coarse graining works for structure. The bad news is, if you do the dynamics, it doesn't quite work. It speeds it up in a way that's not quite controlled. And we were able to identify a way that in this system, and this was the work with Matt Hagee, we could reintroduce additional terms into the equations of motion to get it to be controlled and to give us the same rates and relaxations. And then as we start to use this to get what we call dynamical consistency, we're trying to expand that to all sorts of coarse graining techniques, which potentially suffer from the lack of dynamical consistency. And so if, we can talk about the so-called Martini models or distributed particle dynamics. All of those play with the timescales in a way that you're not quite sure what the new timescales really are. You can compare it to experiments, you can benchmark, and from that infer it. We really need to do a bit better if we're going to be able to deal with the challenge of going from hundreds of particles to moles of particles. Okay, so then another problem would be that if my system, instead of being structured because it has different decorations, what if it's structured because it has a different shape? In this case, what happens is that this particle, because it's a rod, can, in the solvent, essentially direct its motion. It's trapped like a rod. It bounces by the solvent that it's inside. It's very hard for it to rotate, but it's easy for it to go forward. So it turns out that a rod in a bath of spherical particles tends to, under the right conditions, tends to move straighter than you might have thought. And so, again, here, that's an evidence of the fact that by controlling something about the particle, the structure, or how it interacts with others, you can control its dynamics, the science that it does. This was work of Ashley Tucker and now Ben Mahala. Ashley was a PhD student with me about 4 or 5 years ago, went off to do a postdoc, and is now living in Utah. Moving to another scale, even longer scale, we start to think about protein. Oh, sorry, this doesn't look as good as I had hoped. This is a ball and stick rendering of neuropeptide Y. It's a protein that a friend of mine at Kimberly-Clark brought to my attention almost 10 years ago. And he said, well, I want to understand how neuropeptide Y works. I have reasons. I'm not going to tell you what they are, but I have reasons that I want to understand what they are. Neuropeptide Y binds in the brain, in certain ways, and I'd like to know when it binds, does it bind as a monomer or as a dimer? And so we worked with him to identify how this peptide opened up or not, and this is a rendering, and based on that, what the timescales would be of it opening up, so that it would, if it bound as a dimer or as a monomer, once it bound, it did bind as an open form monomer or a closed form monomer. That was actually the question, not just as a dimer, but as an open or closed form monomer. And to do that, we needed to get the energetics. It turned out that the methods that were available then to obtain energetics were too slow. The system was too large, it had hundreds of thousands of atoms, we needed to speed it up in some way. And so we developed a technique that we call adaptive thermodynamics. This started with Gunnar Ozer, who's now in New York, and then got taken up by Haley Bureau, Dr. Haley Bureau, who just received her PhD a few months ago. She's my last Georgia Tech PhD. She's going to be a patent lawyer. Very happy she is as a patent lawyer. And then Dr. Kaylee Allen together, and Noah Stanko is an undergraduate working in my laboratory from Johns Hopkins. What we've been working on is how to pull this protein apart, get the energetics of it, and then use that to be able to say something about the dynamics. And the cute idea here was that the techniques that were known for doing this were using non-equilibrium methods. And what you do is you take the protein and you pull it apart. And you calculate how much energy it took to do it once. Then you do it again, and then you do it again, and then you do it again. Turns out if you average that, if you have enough of them, there's something called the Jarzynski equality, and it tells you, it's going to give you the answer. And so what you see here are these streams of these energetics as we're pulling them apart. When you take the average, the ones that are the lowest in energy of those poles are the ones that contribute the most. So you see that in this case, in this average, that is roughly here, it's getting contributions from only about 2 or 3 of these trajectories. Most of those are not contributing. You spend a lot of time on the computer to generate all of those trajectories. That's sort of all of those little spaghetti strands. Only a few contribute, and if you only have a few contributing, you don't get very accurate averages. So what we realized is that what we were doing was taking a fan. Now when you're an American and you think of a fan, you think of something that does this. But I grew up in Latin American countries where when I think of a fan, I think of an abanico. And an abanico is something that you sort of open up. And I thought to myself, well, what the problem is, it's opening up and it's not closing. So why don't I, with my students, why don't we open it up for a little bit of time and close it up again? And then open it up and then close it, open it up and then close it. And when you open it, don't let it open so much that it gets all crazy and you don't have lots of contributions. So in the staged approach, using that metaphor, in a series of opening and closings of our fans, of our abanicos, we're able to get much more accuracy. We're getting many more trajectories in each one of those windows that's contributing. So maybe not an idea that you wouldn't have thought of if you didn't know about abanicos, but certainly made it a lot easier. One other dream that we had is if we want to go from small to large length scales, there's this theory that tells us exactly what happens in continuum fluids. It's called hydrodynamics. The Navier-Stokes equations are extremely powerful, and they don't know anything about the atoms and the molecules. As a chemist, that should be the most infuriating theory ever, right? Because you modify the atoms and molecules in the system, and all that it does is it changes some constitutive parameter, and then you go forward and you do engineering or fluid dynamics. There must be a way to connect, and in particular, if there are discontinuities in the behavior of that theory that require, then there should be a way that we should be able to predict it from understanding the atomic and molecular properties. So moving from multi-scale like molecular dynamics to hydrodynamics is a challenge that our community should be a part of. And so working with my research scientist, Alex Popov, we've been trying to bridge exactly that gap. So it's another multi-scale gap. And we've developed some techniques that allow us to understand that. I've intentionally not included any references in any of these slides because I knew none of you were going to write it down. But if you want any of those references, you can either just send me an email, or I can direct you to those, And so we're doing this work as well. And this was work that was funded by the Air Force. And everywhere along there were little pictures there that were telling you who was funding that work. Thankfully, we had the funds to be able to do the work. Another direction that I got very interested in many years ago was trying to understand why our community of science was now more diverse. When you look at a lab, like this Lego lab here, why are the scientists that you usually picture these sort of white looking, this is, yellow Lego is white, and with mad hair, which by the way, that's who I think I am here, working on the computer. You don't always think of female scientists in that lab. And the Lego Institute created a kit a couple of years ago for to motivate scientists and say, okay, you can be a female scientist, you can be a chemist or a astronomer or a geologist. And those were, I'm sorry, not a geologist, but those were in that kit. And there was a couple of things that were sad about that kit. It was sold out immediately, which meant that in the Lego world, female scientists were still rare. That was sad. Another sad thing is I just noticed that they were all Lego white, so they only had diversity along gender. They were only in experimentalists. I wanted to have some theorists and computational people. So there's lots of different ways in which we can add diversity, and we need to celebrate it. In chemistry departments around the country, the percentage of women, female professors, the top 50 chemistry departments around 2000 was a little bit over 10%. We're now at a little bit around 20% in chemistry, far from 50%. And underrepresented minorities in the last few years, we are a total of about 4%. Again, not lacking the diversity in comparison to our nation. And so the question is, should we just sit around and wait for it to happen accidentally? Or should we be intentional and change and draw the best talent that we are obviously leaving on the table? And so we started the Open Chemistry Collaborative in Diversity, Equity, Oxide to work with department heads and chairs around the country so we could change the climate for how the kinds of people that can do science. So we are all can be comfortable and be part of the table. And we've held 4 workshops with department heads and chairs, and we invite experts from social scientists to come and engage with our community. They see us as a petri dish for their theories and their thoughts, but they also see us as an originator of ideas because of the solutions that we've employed that they might not have known, as well as the way that we make them particular to our profession. So there are some differences in our profession to others, and so we need to find individual solutions. And we work with diversity communities as well. Very important to remember that every single person has to be at the table. If white men are not part of the solution, there's no solution. So white men have to be in there to be part of the diverse community. So when you think of diversity candidates, it's every one of us. Okay. What makes it not diverse is if every one of us is the same. Another area where I felt that we could do some change is in academic leadership. I've been dabbling with academic leadership through my work with the American Chemical Society as a district director, as a director of Oxide through several activities. And as part of the Research Corporation Control Scholars, that community, and I've been involved with that community as well, has been trying to help academia understand the importance of teaching. And so when you think about having a faculty member who's going to get tenure, is she or he only rewarded for their research? Or she or he also required and expected to teach at a level that's comparable to their research in these leading active institutions? I believe that what makes a research institution, a research university great, is that we have scientists that are at the front of research and that they share that passion and that knowledge with students that can then take it forward. Okay, that's the differentiator for research-intensive institutions. And so if those faculty don't engage with the students or aren't able to engage with the students, then that research institution is not as great as it could be otherwise. Part of motivating that kind of thought that we should have a value and understand how to value education in research institutions would be to train the existing leaders. Well, I'm not sure about you, but it's hard to call up a president of a university and tell her or him how they should start running their university. But if I can get someone that will be a president, who believes in the importance of education and research and the integration of those two, and help them become a leader, then I can have that conversation very easily because they're already on board. So this academic leadership training workshop that we started was in large part aimed at mid-career faculty who were successful in research, successful in education, and were willing to consider being an academic leader. An academic leader could be a department head, a dean, or a research center director. And what we did is we developed a workshop that takes 3 days. And in 3 days, we have learning objectives, because we're teaching, so we need to have learning objectives. For every one of our learning objectives, such as leading and managing above and below you, fundraising, managing outreach, diversity, and legal concerns, engaging and motivating colleagues and staff, etc. For every one of those learning objectives, for 2 different workshops that we've run, for every one, post to pre to post surveys, we went up, self-reported, over 1 point for every learning objective on a 5-point scale, for their understanding of the topic and their awareness of the topic. So we feel that that was a very successful program. They pay about $800 to $900 to come to the program. They pay their way there. We cover their costs when they're there. Part of what we do is we run an exercise where we interview them and we help them understand how to interview for an academic leadership job. The people that are the facilitators are experienced academic leaders who have held research academic positions either as department heads, deans, provosts, a couple of presidents, and center directors. So it also networks, and they keep coming back. We've just written an article on this, and it will be available within within a month or two at ACS Symposium Series as well. So you can see exactly what it was. And when we wrote it, we only had the data for 2016, and so it only includes the 2016 data, but the 2017 data was just as good. We will run this again in February of 2018. And then, so I moved to Hopkins for many reasons. I'll say a bit more about it. But one of them was to rethink my science and rethink how science can be done. And one of the issues I said earlier was that I liked to do theoretical computational chemistry because I wanted to think about a problem. I didn't want to think about the problem just because it was the one that I had the tool for. As chemists, collectively, we have a lot of abilities to solve very, very broad problems. But I don't know how to make molecules. I'm not an organic chemist. I don't know how to run an X-ray crystallography system to identify what's in that, in what material I've just made. But together we do know. So the idea is, let's not think about chemistry so divided into our different disciplines that we can't talk to each other, but that we remember that there's only one chemistry, and that together we can solve much broader problems. And so we founded what we call the One Chemistry Symposium. And in this One Chemistry Symposium, the idea is to bring experts from very different areas to talk about addressing a challenge problem that maybe we haven't yet, that hasn't been solved, and that chemistry could play a role in solving. Possible outcomes can include new collaborations that are as small as pairwise, or collaborations that are as big as a center, 5, 10, 20 people, that wouldn't have happened otherwise. For the first symposium that we ran, we chose the topic, Chemistry's Role in the Brain Initiative. We brought 6 scientists, 3 from outside Hopkins, 3 from within Hopkins, across a range of areas. We had an inorganic chemist, we had a biochemist, we had an engineer who's interested in the connectivity in the brain, we had psychologists, we even had a chemist. And we invited the entire community to come. We believe in food, so we had a really great reception in the middle of it. And so I wasn't thinking just about that one, but now the students know that next year in February or March when we run it again, this is going to be great food. So we're going to get more attendance from the students. We had a dinner reception that night so that the scientists that were involved and some of the scientists from Hopkins could get to know each other a little bit better. Because we believe that collaborations start when you like each other. And then the next day we had a brainstorming session to identify what challenges and what approaches we could use to solve it. We had a huge buy-in from the upper administration in seeing this as a way to generate new science that wouldn't have happened otherwise. And I believe that at Hopkins, one of my opportunities is that we have some great scientists that have tended to have worked in individual silos. And through this and other ways, we might be able to, at least in my department, we might be able to have broader programs. And I think that that's catching. It's contagious. In March of 2018, actually, I know the date, March 6 to 7, the topic will be designing environmentally sustainable nanoparticles. And so that resonates with our work from the CSN. So whereas this project was, that area was not one that resonated with my science, this one will be. But I look forward to the one in the 3rd, the 4th, and the 5th years that may not resonate at all with my science, but where I will still learn something, and my colleagues will do other things. I've written about this in a comment in CNE News, Chemical Engineering News, and we've gotten buy-in from the Gordon Betty Moore Foundation as a way to stimulate new ideas. So that's my 17 vignettes. And we could stop here, but I wanted to just add a little bit to make it so go back to the personal. I talked earlier about the diversity of the scientists that have been Herty awardees. And so I thought to myself, what do you picture when you picture a scientist or a Herty medalist? Do you picture someone that looks like this, who couldn't even speak English when he was 3 or 4 years old? Do you picture someone that looks like you'd be afraid of seeing in the middle of the night if it was dark, as did many of my colleagues at Princeton just 6 months after that picture was taken, when I would walk on campus and they would walk a little bit faster if they're in front of me or a little bit slower if they were behind me. Or do you picture someone who's breaking 2 bricks on his way to getting his, in that case I think my 2nd degree in black belt in Taekwondo. And when you picture someone who's getting a 2nd degree in black belt, do you picture someone who wants to break things, or someone who's a father who is doing that to be with his son? So when you see a picture, when you see someone, you fill in with your own implicit biases what that person is or isn't. But actually we're much broader than that. And just like each one of you is much broader than what we see, and you know your breadth, we should expect the same breadth from each other. And so, what does a Herty medalist look like? It looks like all of these. And not only is that important for me and for my son, but it's important for a chemistry, like a freshman here, Josephine, who was thinking about being a chemist for the rest of her life. If she thinks that being a chemist means that you have to have hair like Al Einstein, and that you have to be in the lab every minute of the day, and that you do nothing other than that, what are the chances that she's going to say, I want to stick around for it? So we owe it not just to ourselves, but to the next generation to let them know that scientists are broader than just the science that we do, and that makes our science stronger, not weaker. At Georgia Tech, I had 20 great years. Some interesting things happened in my family. And I was truly touched because as I left after being there for 20 years, oftentimes when you leave a place, things leave in a way that are not so positive because it's like a divorce. But if you separate from someone and you do it for all the right reasons, or in this case, they saw that there was an opportunity for me to expand my career. I saw that there were opportunities for chemistry to double down in directions that were different than the directions I was going in. That's great. And we could do it civilly and respectfully. Then they throw you a party because it celebrates the 20 years that you had together. And I think that's part of how and I will always think of my time at Tech fondly, because it's where I started my career and where I build others, but they build me too. Moving from Atlanta to Baltimore has been an interesting stage. Thomas Mann in A Man in, no, not Thomas Mann, sorry, in A Man in Full. Thomas Wolfe, thank you, Freudian slip there. Thomas Wolfe, in A Man in Full, wrote that the Georgia Tech's campus was sort of a manicured suburban campus that happened to be framed by tall skyscrapers. Well, so at Hopkins, we have that kind of suburban feel, and only 3 miles away we have the skyscrapers. So I haven't quite lost my Atlanta connection to Georgia Tech in moving to Hopkins. And there's even, as I was talking with some of my colleagues here from Emory, there's a feeling around the campus that feels very much like Emory's campus. And indeed, even the Georgia Tech campus is starting to have, as they've really manicured and landscaped the campus to be much more of an area where, when you think of that modern, of an old university, a university where students think and play, and because they play, they can think more. And so that's something that we have there as well. My students are what's made all of the work that I've done possible. It was very important for me that my students came with me to Johns Hopkins, and so as part of the process of moving to Hopkins, we had a retreat at Johns Hopkins in the March of the year that we were thinking about moving, so they would get to know Hopkins, and Hopkins would get to know them. And I believe that that's a consequence of a reason why they went. Many of them went with me and continued to work. And so there was very little dip or change in the size of my group. Actually, it got bigger. And our research productivity over the last 2 years has actually gone better, has gone higher. And so I didn't move to work less hard. I moved to think harder and to be more challenged and to challenge my students. And so I hope that you have gotten the sense that theoretical and computational chemistry can be used to address many different problems. It's fun to do it. There are lots of grand challenges available. There's a Nobel Prize that was given supposedly for multi-scale chemistry to Warshall, Levy, and Karplus, and they deserve the credit that they got, but they solved the problem of multi-scales where they connected electrons to nuclei. We still need to connect nuclei to human scales. And so if you only care about Nobel Prizes, you're a young person, there's still a lot of opportunity. And, but none of this is possible if we don't advance people. And we advance people in the way that we work with each other, in the systems that we do. Working with the Georgia local section for almost 20 years, that's how I learned the importance of advancing people. I learned a lot of how to be a leader by seeing the other leaders in our section, them telling me and having the I don't know, bravado to tell me when I was wrong, and to also let me know when the way I was exerting my leadership was not effective. If people don't tell you when you're wrong, and if you don't listen to when you're wrong, then how can you ever be right? And how can you ever do it right? And so I owe the Georgia section a lot for my success, not just for awarding me the Herty Medal. And so to conclude, not just thanking them, I want to thank all of the members of my group, my current collaborators, my wife, my son, and all of the people, all the organizations that have funded our science. And with that, I will be happy to answer any questions.
Questions?
You mean you've done something wrong?
Did I do something wrong?
Yes. Tom Wolfe wrote A Man in Full, not Thomas Wolfe.
There you go. Thank you, Tom Wolfe. That I did something wrong. You never know, right? When I talk to students, let's say in high school, when they're looking at colleges, I tell them that the decision that they're making is both the most difficult decision they're going to make and the easiest. It's the most difficult one because they have to make a choice. It's the easiest because it doesn't matter what choice they make, it will be the right choice. Because they will go to a place that will help them go to the next stage in their career. The only mistake that they can make is if they start to focus on the what if, instead of focusing on the opportunity and possibility of where they are. Right? So yes, I can go through and think about, could I have done this, could I have done that? But actually it would be a mistake to worry about whether or not that was a mistake.
Right.
Rigo, you know, some Hollywood directors have produced some movies lately that they say they were waiting for the technology. You know, they always had the idea, but they were waiting for the technology to catch up with them. Have you been in a situation where 25 years ago you thought of a problem and you just didn't have the computer power to solve?
Yeah, and sometimes you're still stubborn and you keep working on it anyway. So this problem with the neuropeptide Y, when we first started working on it, the problem was that doing one single simulation at room temperature, we could do it maybe for a nanosecond. And what did it do? Nothing. So what we did was we sped it up to a hotter temperature. We started with 50 degrees, 50 more degrees. We finally got to about 500 degrees Kelvin in water. And then it did something. I don't know. Yeah, in water, right? We were able to, and still only do 1 nanosecond. Right? We were able to say something about it and infer it, and then use that trajectory to then do other things. So it was great that we could do that. But that simulation today would be easy. And now we can do many more of those simulations. And we can get real statistics and have a better appreciation. We still use that model because it lets us test for larger molecules where we wouldn't be able to do the long time. So I think that's an example. There's a lot that many of my colleagues are dreaming about being able to simulate a cell, where every single atom is named, or at least almost named through coarse graining. That's something that wasn't even dreamable 10 years ago, let alone 20 years ago, impossible, but even 10 years ago. Now we can dream about doing it for maybe a second or a millisecond once on like all of the world's computers for a year, which is kind of what Anton was. All right, so there's still more that has to be done because just one trajectory isn't enough, and even storing the data is difficult. And so I think that with the emerging tools that we're learning from machine learning and data science, it will allow us to infer, do new numerical experiments, and in turn that will allow us to develop mesoscale theories that will allow us to understand and have a broader and be able to solve larger problems that we can't even address today. So it's not just solving the computations, we have to help use that to help advance the theory as well.
The chemical industry is making polyethylene, polystyrene, polyesters, and we're filling the world with those products. Is any work being done on the decomposition of those plastics, similar to the way nature decomposes wood, decomposes animals?
Yeah, so that's a great question. So that's not a question that I'm working on right now, but it is a question that the chemical community is aware of. There's these so-called Centers for Chemical Innovation. The National Science Foundation funds about 10 of them over the course. There are 5 to 10 year lifetime center, and at any given time there's 10 of them because they start every year. One of those Centers for Chemical Innovation is called the Center for Sustainable Polymers, CSP. It's based out of Minnesota. Mm-hmm. And their goal really is to develop polymer solutions that are either biodegradable or easily repurposed, right? So and we have to think about that. You may not necessarily want to decompose, because think about all the energy that it took to make them in the first place. So if you decompose completely to atoms or small monomers, you've taken up all of that energy as well. So if we could not completely decompose, but reformulate, reshape in a way that gives us like a reuse or a recycle, but at the polymer level or molecular level, that could also be advantageous. So there are several strategies that are being employed. They're working on some of those strategies as one example.
Okay,
Thank you for the question.
Move on with the rest of the program since the hour is getting late. So I've been to a lot of these Herty Award dinners before, and it always struck me that this was sort of like your thesis defense. So you give the presentation, and then you're given your diploma, so to speak. So we do have the award to give you. But so as Rigoberto already knows, we also give out a copy of Crusading for Chemistry, which is the biography of Charles Herty. I don't know if you already have a copy.
I don't.
Unbelievable. Very good copy.
Thank you. I always read the Cliff Notes written by Don.
And then, of course, the actual Herty Award, which you saw the picture of in Rigoberto's presentation, but here is the actual gold medal, which will be yours as a reminder of winning this prestigious award. So,
Thank you.
congratulations.
Oh no. So, Amy, did you get it?
I did.
Because that's the one that goes on Facebook.
I'm going to turn it back over to Ron for any final announcements.
Okay, we have one more thing to give you, Rigoberto. So Don Hicks has it's all chemistry mathematics, and he told me to let everyone know this is number 12,050 of these given to chemists and teachers over the last 10 years. So we definitely want to give you.
Yeah. Let me shake your hand.
I want to thank everyone for coming out. We did put evaluations on every table. We're trying to make sure we improve the event and work together as a section to do that, so your input is really valuable, especially for next year. Thank you again. Drive safely on your way home.